Good afternoon. It's a pleasure to introduce you Marcello Carioni, and I'm going to tell you something about his research life. He did his PhD at Max Planck in Leipzig. Then he did a postdoc at Graz with Christian Bredis. And now he's a Newton International Fellow at Cambridge with Carola Schölleb. And he recently got a position as an assistant professor at Twente in Netherlands. Today he's going to present a talk about sparsity and convergence analysis of generalized conditional gradient methods. Thank you very much.
Thank you very much for the introduction and also for the invitation. So today I would like to talk a little bit about the projects that we had in collaborations with people, mostly people from Graz, Christian Bredis, Silvio Fanzon, Francisco Romero, and Daniel Walter. And as you can see from the title, actually the main topic is going to be generalized conditional gradient methods. And I would like also to highlight some sparsity kind of properties of this kind of algorithm. So let me start briefly with the summary. So I'm going to talk, first I'm going to introduce some Frank-Wolf algorithms, so like the basic form in finite dimensional setting. Then I'm going to basically explain how to generalize that to infinite dimensional spaces and the space of measures. And then I'm going to define our main setting that with basically arbitrary convex regularizers and highlight the sparsity properties and convergence rates. And finally, if I have time, I think I will talk a little bit about dynamic inverse problems that basically can be encoded in this kind of Frank-Wolf type framework. And I'm going to present some numerical simulations. So let me start with this is the basic Frank-Wolf algorithm. So basically, you want to minimize a convex function over a convex set in a finite dimensional set. F is regular enough, and then you also need C it's compact, and then you basically would like to solve this minimization problem by constructing an iterate in this way. So first you solve, you take the iterate xn, and then you solve the partially linearized problem in xn. So basically you take, you linearize f, so you take the gradient of f, and then you compute the minimizer in C of this linearized function f. And then you compute basically this minimizer. And then you construct the next iterate basically by interpolating between the previous one and these new inserted points that you found. And then you optimize with respect to the interpolation coefficient, and basically you find the next, in a suitable way, so that basically you decrease the energy. And then in this way, basically you find the next one. So, I'm going to talk about these two steps. So the first one is usually referred to as insertion step, and the second one as coefficients optimization step, because you would like to optimize the coefficients of this linear combination. So this is the main idea. So there has been a lot of works about this topic. It's the natural convergence rate that you have, it's sublinear, but usually you can improve that to linear convergence rate in finite dimensional setting if you suppose some strong complexity of f, or you have some better interpolation strategies. And also this algorithm can be quite easily generalized to infinite dimensional spaces like Hilbert, Banach spaces, and these are usually referred to as generalized conditional gradient methods. And also, so you can also show that basically very famous algorithms for sparsity can be interpreted as Frank-Wolf type algorithms. There are several examples of that, and usually they all based on some sparsity, some sparsity in the iterations. But okay, I would like basically not to spend too much time on this kind of informations about, let's say, the finite dimensional setting and the names, and I would like basically to take one of the most recent and probably most famous conditional gradient methods in the space of measure. So what you want to solve in this case, it's actually a problem that is very similar to the previous one. So you consider the space of measures, and then you would like to minimize the sum of two terms. One is sort of fidelity term, so FAU, so you can think about that as a fidelity for inverse problems, for example. And then you have some regularization that is the total variation of U. So here A, it's you suppose it is a linear, weak star continuous, y it's an Hilbert space, and f is some discrepancies that, I mean, is usually you suppose strictly convex and smooth. So, and then you would like to basically to define the same, so a similar generalized conditional gradient methods or Frank-Wolf type algorithms for this problem. And what you do, it's basically very similar to what I described for the Frank-Wolf. So you first solve an insertion step, and basically the idea is the same. So you linearize the first part of the fidelity term. So you take the gradient of f composed with a, and you take basically this linearization, and still you keep the regularization, so the total variation. So you still minimize the total variation. So basically, this is the same as before, with the only difference is that, so instead of having minimizing over the convex set C, you have like a convex penalty that is the total variation in the space of measure. And then, after you do that, you basically do the same coefficient optimization step. So you construct the interpolation between the previous iterate and the new point that you found, and then you optimize with respect to the parameter S, and then you construct the new iterate. So that's the idea. So these actually can be defined well, and this is actually the starting point for this generalized conditional gradient method. But the observation that one can make is that so the iterate un that you can construct in this way, so you can construct this iterate as a combination of Dirac deltas. So basically your iterate will be like this linear combination with respect to some weight C of Dirac deltas concentrated in the points of the domain. And why is that? Because basically you have this kind of, I would say, basic lemma of convex analysis that tells you the following. So here I'm defining, it's common to define the Pn, the gradient of f composed A in the point un, so basically your linearization. And then once you do that, basically what you find in the lemma is exactly the insertion step. And the point is that the solution of this insertion step, of this partially linearized problem, can be found as a multiple of the Dirac delta for a point in the domain omega. And you can even characterize this point because this is exactly the point where Pn, so where the modulus of Pn has its maximum there. Okay, so this is actually very nice because so in this way basically you can say, okay, I'm not searching like for any minimizer in the space of function for the insertion step, but I'm searching for this particular delta at x, and then I add this Dirac delta in my iterations and I construct the iteration in this way. So at this point basically you construct the iterate just by adding this new Dirac delta with suitable coefficients. So in the end, your iteration would look like a linear combination of Dirac deltas, like this picture, and this will eventually converge weakly star to the solution of in the space of measure. So the Dirac delta will basically concentrate if you have like a diffuse measure, and then you will converge to the solution of your optimization problem. And this has been proven so by Bredes-Pikaranian. I mean, there's also like a similar work by Boyd, Schebinger, and Recht. And what you can prove is that if you construct un in this way by adding these Dirac deltas at every step, then you weakly star converge to a minimizer of G. And also the convergence rate, it's a sublinear convergence rate. So the one that you expect also from standard Frank-Wolf type algorithm. And this is actually basically the story of how you can define this kind of sparsity, like optimization algorithm in the space of measures. So there's some remarks about that. So as I said, actually these algorithms use like deeply the sparsity of the problem because you construct iterates that are sparse, so that are a combination of Dirac deltas. Also, what is nice about this kind of algorithms is that they are grid-free. So in the sense that you don't need to discretize a priori your domain, but you can choose the Dirac delta as you prefer in the domain. So basically this is nice because if you want to reconstruct spikes in your domain, then it's nice not to have to prescribe the grid, because perhaps your spike will fall into the points that not on the grid, and then you can have instability, you can have some sort of diffuse effect around the Dirac delta. And this is quite useful. Also, something that will be useful for later, you can improve the coefficient optimization step instead of taking, so basically you can do a lot of things. I mean, instead of taking this kind of interpolation, you can simply add a direct delta and then optimize all the coefficients in the linear combination, and you optimize that with respect basically to the energy G, so the complete energy. And this is an easy problem because it's basically a finite dimensional problem where you basically just consider the fidelity term because the direct delta basically are linear with respect to the total variation, so it's easy to solve. And this improves over the interpolation step. And this is also needed to prove some linear convergence, as we will see later. Okay, so that's basically the work of Paredes-Picaranian to show actually why this work, how to have sublinear convergence. But it's interesting to notice that so it's actually possible under some assumption to improve this rate to a linear convergence, like for standard Frank-Wolf. And so that's the assumption. I mean, and now I'm going to guide you through all the assumptions that some of them are a little bit technical, but I think the general idea is going to be clear. So we need some strong convexity assumption on the fidelity term. I mean, that's necessary. And also we need some sort of structural assumption on the dual variable of the minimizer of the energy G. So the dual variable is going to be P star, so I define like that. It's just the linearization of the fidelity term computed in the minimizer. And then you assume the following hypothesis. So first of all, you need strong convexity of F. That's something that you always need. Then you need that there exists a set of point xi such that the maximum of the dual variable of the absolute value of the dual variable in the point x is exactly achieved on this set of points. And also you need that if you basically A of the direct deltas in this point xi are linearly independent. Now, I mean, if you think a little bit about this hypothesis, you can actually realize that if you assume all these three hypotheses, then you immediately have the existence of a unique minimizer that it's sparse in the sense that it's given by this linear combination of some weights, and then the direct deltas where you take basically the maximum of the dual variable. So basically this assumption is basically telling you that you have just one minimizer, that it's sparse, and then it's given by this linear combination of direct deltas. So that's the first set of assumption. Then what you need, it's also some, I mean, this is actually some second order condition on the dual certificate or the dual variable P bar. And this is actually quite classical in the theory of super resolution. I mean, it's some sort of second, basically you prescribe that at the extreme of the function P bar, the function is basically strongly convex, locally strongly convex, or locally strongly concave with this rate theta. And so this is actually something very classical also if you want to super resolve with respect to noise and you want to stability with respect to noise. And then finally, you need some sort of high regularity of A in with respect to some Lipschitz norm. So, I mean, you can formulate that easily, but just by requiring that if you compute A on delta xi, that are the points where you are supported, minus delta x, this is less or equal than a constant times the distance between x and xi. And this can work locally around the point xi that you prescribe at the beginning. So these are actually some of them quite technical assumptions, but so the important thing is that what you need for doing something like that is strong convexity of the fidelity term, uniqueness and sparsity of the minimizer, and some second order condition of the dual variable and higher regularity of A. And this set of assumptions, it's basically giving you a linear convergence. And this is like a work by Pieper and Walter, and also like parallelly by Flint, De Grune, and Weiss. And they prove basically that if you have this set of assumptions, or I mean like slightly different between the two papers, but nothing massive. Then you have linear convergence rate, and with this linear convergence rate with this zeta between 1/2 and 1. And that's basically the story about linear convergence rate for this kind of problems in the space of measures. So what we are interested to do now, it's basically try to think of what, yeah, sure. Mm-hmm. Yeah. The last you mean higher regularity of A? Okay, the second order condition of the dual variable. I mean, from my experience, something that somehow it's quite technical and you need to check. I mean, I don't know an example of some kind of particular situation where you have that. Basically, so you have your dual variable oscillating between +1 and -1, maximum and minimum, and you need some sort of non-degeneracy at at -1 and +1. Yes, I think so. I mean, it's not so. I mean, here it's. Yeah, I'm not so sure. I mean, I'm not able to give you an example that will really illustrate why this condition is really necessary. And the second one, it's actually perhaps easier to show. I mean, for example, you need the kernel. So I mean, this is equivalent to basically some sort of continuity of the adjoint with respect to Lipschitz. And you could have a kernel, for example, that depends continuously on X, something like that. Yeah. Okay. So what we were interested to do is basically to answer the same question or try to build the same framework for general inverse problems. So basically, same fidelity term, but working in Banach spaces and regularizers, so convex regularizers. So namely, we consider these kind of problems. So we have fidelity term as before, and we have R that instead of the total variation as it was before, it's a convex regularizer. And X here is some separable Banach spaces with a pre-dual X star, and R it's a convex, one homogeneous, and coercive. So I mean, probably coercive perhaps you can work in some quotient spaces, but right now we just took coercive, and I mean, because it's quite simplified a lot everything. And so what we did was the following. So we just simply defined the same generalized conditional ingredient methods for this case. And so you can define that basically in the same way, because you can just compute the partially linearized problem as before. So you linearize the f composed with A, and then you solve the partially linearized problem. And then you do some coefficient optimization step in the way that you prefer. And then you basically have defined the generalized conditional gradient methods for this case. Now, the interesting thing is understand how sparsity enters in this definition of generalized conditional gradient method. And so before we had iterates that were direct deltas, and now we basically observe that we have a more general version of the previous key lemma, because we have the following. So if you solve this partially linearized problem, that is the same as always, basically, then you can find a solution that is given by a multiple of v bar that is an element in the extremal point of the unit ball of R. And this is actually also like a quite simple convex, convex theorem, convex lemma. And just to remind you, the extremal points are just the points of a set that cannot be expressed as a proper convex combination of other 2 points. So if you have a polygon, for example, all the vertices are the extremal points, and then the other points are not extremal points because you can express that as a proper convex combination. So by this lemma, basically, you can see that, so in the insertion step, basically, you can find a minimizer that it's an extremal point of the unit ball of the regularizer. So you can say that at every iteration step, you want to add an extremal point of the unit ball of R to your iteration. And if you do something like that, then basically, so the iterate that you construct are sparse in the sense that are just a linear combination of the extremal points of the ball of the regularizer. And then this basically generalizes this notion of sparsity that you have in this optimizations algorithm. So then what you do is the following. So basically what I explained. So you define the ball of the regularizer as B. And then you take iterates that are of the form as linear combination of extremal point of B. And then you compute the next iteration just by solving the insertion step. So basically, you compute the insertion step, but restricting yourself into the set of extremal points, because then you know that there exist solutions. And then you do some of the coefficients optimization step in this way, like we optimize with respect to the all linear combination, but you can do different things. And then, in this way, you have defined like a generalized conditional gradient method that consists into inserting extremal points at each iteration. So what you can immediately prove is some worst-case convergence rate. So you can, this is not so difficult. We did that in a kind of a different way because we needed something else, but this could be done even like directly. And you can prove that the convergence is sublinear, so let's say the rate of convergence is sublinear, and UN weakly star converge to a minimizer. So some remark. So this basically recovers the generalized conditional gradient methods for the minimization of the total variation, because so you have this result that the extremal point of the unit ball of the total variations are plus minus the direct deltas in the points of the domain. So basically, if you take the atoms, so the iterates that you are adding, so for this general case, then you realize that when you take as regularized the total variation, then you get direct deltas, and then you recover the previous algorithm. You can also define more general algorithms, so that, for example, later, if I have time, I'm going to talk about dynamic optimal transport, and you can do that, for example, or you can do some group sparsity regularizer, PD constraint inverse problems. I mean, there are several examples. I mean, the main difficulty is that sometimes you don't know how to characterize the extremal points, so it's not always so easy to find like a nice algorithm that works well in practice. And also, like, it's nice to remark that you kind of see from this algorithm that this sort of notion of sparsity as extremal point of the ball of regularizers enters into this the construction of this kind of algorithm. So this is actually all about the worst case convergence rate, so sublinear convergence rate. Now we would like to understand and to understand how to prove and to make suitable assumption to prove linear convergence. And so the set of assumption is similar somehow, but I think it's nice to have to check the two set of assumption, like for measures and for this general case at the same time. So first, you need again the strong convexity of F, and again some sort of like this uniqueness sparsity for the minimizer. So in this case, you require that you have a set of extremal points, such that basically if you compute this, now this is the duality product, x star and x, and you compute the maximum of among all the. I mean, okay, here it's a little bit technical why I'm taking the weak star closure of the extremal points, but so you can just think right now that these are just you take the maximum for the extremal point of this duality product, and you get exactly the points that you prescribe at the beginning. And also, you need that this is the same assumption as before, so that AUI is linearly independent in Y. Okay, so again, as before, this implies that the minimizer is unique and it's sparse in the sense that it's given by a linear combination of extremal points. So then we need some second order condition on a dual variable again, and some higher regularity of A. So for that, actually before we add some, let's say, second order condition with respect to basically the metric in RD. So here basically we need to find a metric on the extremal point. I mean, it's not a metric in general, but you can think about that as a metric, this function G. And what you require is that your duality product P bar U is actually satisfy the second order optimality condition with respect to this metric G that you defined. And also you have this higher regularity of A, again with respect to this metric G. So you have the second order condition, so some sort of strictly convex, strictly concave when you have the duality product is equal to 1. And you have that A ui minus u, it's controlled by G u ui. And then, if you assume all of this, you actually can prove that the convergence is indeed linear and, again, with the same rate as before. So, okay, so let me so this is the result. I think even more interesting than the result is actually how we prove that, because I think this is a general strategy that could be interesting in general. And we did that by basically lifting the problem to the space of measures defined on the extremal points. So we have actually our sparse problem that take into account extremal points. And now we would like basically to rewrite this problem in an equivalent way, but as a minimization of measures that are supported on the extremal points, and then prove convergence in this lifted space, and then coming back to the original space. So how we do that? So just some definition. So we consider this W is the space where we take measures, and we take basically the extremal points and we close them in the weak star topologies because we need some sort of like nice separable metric space. And then we consider positive measures on this set of the closure of these extremal points. So this is our set where we take measures, and then we would like a way basically to pass from measures defined on extremal points to linear combination of extremal points. And actually the formal way to do that, it's actually by some sort of using, this is some sort of, let's say, Shuke theory machinery. And the idea is the following. So you have a measure on W, and then you find U by basically computing some sort of weak barycenter of the measure mu. So this is, if you don't have like the test function with respect to P, this is just the barycenter of the measure mu. And then you would like basically to construct measures and elements in X by constructing pairs of barycenter and measures that in kind of surjective way, let's say. So just to clarify that a little bit, so we would like this correspondence. So given a linear combination of extremal points in X, we would like basically to lift that to measures that are linear combination of direct deltas concentrated on extremal points. And we would like to be able to kind of given a measure to find a U, and given a nu to find a measure, so that we can basically have a surjection between the two spaces. And it's possible to do that, and this is basically the result of the so-called Shuke theorem. And what you have is the following, basically. So if you have a measure in this set of extremal point, then, it's easy to see that if you take the barycenter, then the regularizer of the barycenter, it's less or equal to the total variation of the measure. But also vice versa, this is the Shuke theorem. If you take an element, U in X, that is in the domain of R, then you can find a measure concentrated on extremal point, such that it represents U, and you have that the regularizer is exactly equal to the total variation of mu. And this basically allows to define and prove the equivalence of this lifted variational problem. So, this problem is basically you take measures in M plus of V, and then you define some lifting of the linear operator A at, and then you just basically regularized with respect to the total variation in this space of measures supported on extremal points. Yep. Yeah, B it's the ball of R. So R, yeah, it's yeah, here it's just the unit ball of R. Yeah. So just to have an idea, so we have these two problems. The first one is the original one, and the second one is the lifted one in the space of measures supported on extremal points. And these are, one is the original one, and the other one is the lifted one. And what we can prove is basically that these two problems are equivalent. So basically, if we have a solution of the first one, then you can find a measure that represents this minimizer mu bar, and it's a solution of the second problem. And vice versa, if you have a solution of the second problem, then the weak barycenter is a solution of the first one. So basically, you can prove that these two problems are completely equivalent. And now, the idea would be basically to be able to prove convergence with respect to, so for the generalized conditional gradient methods for the first problem, by proving the same linear convergence with respect for the iterates for the second problem. And that's basically how we did it. And then basically we have just translated the assumptions that we have for that we want to have on our problem to the lifted problem, and then being able to basically pass through from one to the other one. Okay, how much time do I have? 15? 10. Oh. Okay, so then let me go through, give you like an example that, could be interesting. So I have to define a little bit of optimal transport theory, but I think it's going to be actually useful to understand. So, we tried, this is actually worked in the opposite way. So before we try to find a generalized conditional gradient method for dynamic variational inverse problem, and then we basically had the general results later. But okay, so the point was to be able to reconstruct a time-dependent measure given observations kt at each time t. So basically, you have like a time-dependent family of measures, and you have linear observation for every time, and that goes into some ht that are time-dependent family of Hilbert spaces. And then you would like basically to solve the following dynamic variational inverse problem. So you have fidelity term in time, and then you have some optimal transport regularizer that should be able to correlate the observations at different instant of time. And so what we wanted to basically to define, it's a regularizer that it's coming from optimal transport theory, that it's able to basically prescribe some evolution that follows some optimal transport cost, so that minimize some optimal transport cost. Now, so just to kind of remind you a little bit about optimal transport, so optimal transport is just like a way to measure the distance between two probability measures in such a way that basically you can transport one to the other one following, so according to some minimality with respect to some cost. So our cost, we just define the square cost, and then the optimal transport distance is just basically you minimize with respect to all maps that transport one measure into the other one, and you minimize the displacement, so with respect to this cost that you defined. And this is the Wasserstein, basically the Wasserstein distance, or the Monge formulation of optimal transport. So we were interested more in a dynamic formulation of optimal transport in order to kind of have basically some regularization in time of our evolution. And for doing that, actually what you can do is the following. So you define the continuity equation in this way, that is so you take all pairs rho t, that it's like a time-dependent family of measures, and vt that are vector fields, And then you say that this satisfies the continuity equation if this equation is satisfied with initial and final boundary condition. And then it's, I mean, this is a result by Benamou and Bonnier that show that it's equivalent to compute the Monge formulation of optimal transport or minimizing the kinetic energy, that is the first term, the kinetic energy of the pair rho t and vt with respect to all pairs satisfies the continuity equation. So basically, instead of looking at some static formulation of optimal transport, then you look at some dynamic formulation, and basically these two quantities are completely equivalent. So then, but with the difference that the first one actually encodes information in time, so we can use that actually to regularize our optimal transport problem, our dynamic inverse problem. So now you defined, so this is our dynamic inverse problem, and the regularizer is then just so our Benamou-Bonnier energy, so our dynamic formulation of optimal transport, plus some total variation. And so this can be also convexified if you make appropriate substitution and I mean in a proper way, so that basically J alpha beta, it's a good convex regularizer that you can use for inverse problem in a meaningful way. So this is just like a construction. So in the end, what we had was so a standard G that it's made of a fidelity term dependent on T, and a convex regularizer J alpha beta. And so basically we are in the setting that I described before, and we want to apply generalized conditional gradient methods for this problem. And the point is that, so again, as we saw before, we can construct these generalized conditional gradient methods by constructing sparse iterates that are the extremal points of the unit ball of this Benamou-Bonnier energy, so this J alpha beta regularizer. And in this case, it's actually, this is good because we can actually characterize these extremal points. And the extremal points are basically just pairs of measures that are concentrated on curves in the domain. So this is just, so these are time-dependent measures that are basically moving direct deltas in the domain. So this allows you to define like sparse measures and iterates of your generalized conditional gradient methods that are just moving direct deltas like this one. And basically you can construct an algorithm just by adding new curves to your measures according to some kind of to the insertion step, and then building a sequence of time-dependent measures that is converging to the solution of your problem. So just to summarize a little bit and give you some like a numerical result. So we did that. So we basically want to reconstruct that, and we try to reconstruct that by adding absolutely continuous curves and measures concentrated on these curves. And this is some results. So this is the ground truth. And this is the reconstruction that you get if you do a generalized conditional gradient methods for this kind of dynamic inverse problem. As you can see, actually, you have some artifacts when you have some noise, and these are curves that you add to your so curves that you have added during the iteration, but have not erased during the iteration. So you can see some artifacts of this type, and you can see even more artifacts if you change the parameter and you put like 60% of noise into your ground truth. Okay, so that's all. This is some references. So the first one, it's the paper that I talked about at the beginning, where we generalize conditional gradient methods and we prove linear convergence. The second one is for dynamic inverse problems. And then also these are some other references that works that related or that we used for that. Okay, thank you very much for the attention. Mm-hmm. No, I mean, yes. So yeah, the question was if in the linear convergence result that Z that gives basically the convergence ratio, let's say, could depend from some parameters of the problem or some kind of assumption that you can make. We don't know exactly. I mean, for my experience, usually this Z it's actually fairly close to 1/2. So I don't know if I mean you usually get 1/2, or you can have different situation. I mean, at least for the experience that I've seen in the graph of linear convergence, usually it's fairly close to 1/2. But yeah, I'm not sure about. I mean, I don't know if you can say something more, or you can change something. You change some hypothesis.
Yeah, in orthogonal matching pursuit, if I remember well, you add 1 point after the other to recover like a sparse vector. So it reminded me like of your construction. Can you comment on the link?
Yeah, I don't know exactly the techniques that you refer to. It looks so. It's more like you search for projections in your.
Not exactly. I mean, say you want to recover a sparse vector, you don't know what the support is. So the idea is that you first look for one sparse vectors, and so you look for the best entry, like for the for the best index where you put the non-zero component, and then you look for the best non-zero component. Then you fix that, and you look for the next one, and then you keep going.
I see. Yeah.
Yeah. Yeah. You don't have the grid. Okay.
Yeah.
But I mean, if you in this case, if you have like a Banach space, say a finite dimensional space with where R is just the L1 norm, what happens?
Yeah, in this case, in this case,
a dictionary would be finite. Okay.
Yes. Yeah, when you have finite dimensional, I think that you just take the finite collection of external points of your ball, and then you can use that as a finite dictionary, and probably you can you have some very similar thing, I guess.
Thank you.
Yes.
Up to being able to solve the. That was it. I mean, just.
Yeah, I was also wondering about the possibility to like having a conditional gradient methods for measures that kind of represents neural network. But I also have the feeling that the dimension of parameter space is too hard to do something like that. I mean, this was also your impression.
Or I was wondering if the problem is really that the first problem, the one where you have to do the insertion and look for the best, maybe that problem itself, for some reason I don't know, becomes hard, non-feasible somehow. I don't remember. I remember there was in trying to apply to neural network, there was a catch, and I thought the catch was that the one problem, which is kind of the selection step in the orthogonal matching pursuit, but in the continuous setting, becomes tricky because you basically have to search for this one vector, and that's a non-convex problem anyway.
Yeah, exactly. Yeah, when you have
if you wanted the question was, because the truth I don't know is, you have this one step when you linearize, and you have to do the insertion step. But all the rates are up to being able to solve that problem exactly.
Yes.
But that problem, in principle, can be hard, right?
Yes, exactly. That's exactly the catch. Yes.